On this example part, what we can see from an initial look at it is what we think would be quite a simple part to turn. Now if I view from the top of this object, we can see it looks like a simple turned form. However, if we turn off the shading and actually zoom into this region, what we can see is we do have an undercut area that we need to deal with. So, how are we going to attack this? Well, in order to reach this area and machine this region and also an undercut region at the front here, we're going to have to utilize either some special tooling or some kind of special approach. Now let's say, for example, we use, in this first example, it's going to go into the properties, and what we're using is one of these angled turning tools, a 35-degree diamond. Hopefully this will give us some kind of access to these regions whilst giving us clearance on the rest of the job. So if I actually go into a 3D simulation, just play this. Okay. So first issue, you can see we've got a big gouge down the front here. If I view from the top, and just simulate that again, you can see the holder geometry is actually gouging into the front of that part. Also, if I view from the top and just go into a centerline simulation, I'm just going to again just zoom into this region here, turn off the shading and just single step through. So even though the tool geometry will actually fit in this gap, you can see the fixed angle of that orientation as we move into that is actually taking a lot of this edge away as well. So we can machine the rest of this part, but you can see this tooling is not desirable to machine this part. So what if for example, we try and use some different tool geometry? So rather than actually utilizing the tool shape, so this is obviously in a vertical position, let's try utilizing the B-axis. So this time I'm going to turn on this example here. So again, same curve geometry to work with. Into the properties, this time we're using a 35-degree diamond tool, but this time it's a neutral tool. And this neutral tool, if we view the B-axis orientation, so we can see we're using a 45-degree angle. So again, I'm just going to single step through this. So now we've got the right angle to approach inside that region, but now the trailing edge of that tool, or the front edge of that tool, depending on your direction, is actually gouging into the part at this edge. So this is giving us access to the majority of the job, so now we can undercut this undercut region here, machine this undercut region here, but we're still faced with the issue on this section. So what it appears that even though we're trying to utilize tool geometry to fit into these regions, we're going to be better off trying to somehow move the B-axis during that process. Now if we chose to use multiple B-axis orientations, we'd have some kind of join or variation in the tool path between our passes. So what we want to really do is do this in one continuous pass. We can actually utilize our simultaneous B-axis machining to do this. So into the properties of this one, under the finishing tab, so we're using a groove cut tool with the ball nose edge to it. But if I go to the this new tab here, we have a B-axis tab, and in this case we're utilizing the B-axis simultaneous machining. So we've chosen a lead angle of 20 degrees, but we've also chosen to actually work within a limited range of B angle between 65 degrees and 90 degrees. So let's go into our 2D simulation again, step through. So now it's working at the 90 degrees, can tilt over, utilizing that lead angle, machine into that region. Now as it approaches this region here, it tilts back again towards the 90 degrees to try and machine that portion there. Again back to that lead angle of 20 degrees, and then moving down the component to machine inside that other undercut region. So let's look at that on a machine tool just to see what that process looks like. Closing the jaws, and there you can see the simultaneous B-axis machining occurring on that part.